Questions about the previous material before we get started? Okay, well, you can obviously ask later as well. So this lecture will be about sort of the analysis of single objects. And so this continues where we left off from the complex or more advanced segmentation techniques and sort of what we do with the data once we've segmented it. And so we have kind of the workflow again that we've started with the image enhancement. We had the basic and advanced segmentation, so how we actually get the features or the structures out of the images that we're interested in. And now we move to, once we've gotten these segmented regions, what can we actually do with that? And so how can we make a meaningful analysis of what we've taken out? This will start off with what are the very simple or straightforward sort of analyses that we can do. The next lecture will cover some of the more complicated analyses that are possible there. And so that will go over a lot more of the details of complicated shapes and how we can take more meaningful metrics out of that. Then we move on to spatial distribution and the statistics and reproducibility and everything else. Yeah, the dates on here are wrong for whatever reason, but I'll fix that. So the resources for this are very much the same as what we've had before. There's a few new items here. So for principal component analysis, has everyone heard of that before? Eigenvalues, eigenvectors, covariance matrices. Has anyone never heard of those things before? Okay, so we'll have a quick refresher, but most of you should be fairly familiar with it. Then this idea of sort of shape tensors and what they're useful for and where else you can apply them. This is then easier to see in the handouts. And then, sort of the models and ROC curves, because we'll have even more emphasis on that, because that's as important as it always has been. So when we look at sort of the previously topics, as I briefly mentioned, that we had this image enhancement. So this is always the first step that we have. So how can we improve the quality of the image data? How can we get the contrast that we're interested in highlighted and get rid of all the noise possible? Because at the later stages, it can be much more difficult to get rid of that, or much harder to see that that is actually noise. Then how do we understand sort of the histograms? How do we deal with the data that we're working with to segment it? How can we do some of this automatically? How can we do sort of, regions of interest, some contouring and machine learning? How does that sort of fit into these pictures? And the ROC curve, again, to sort of review it, we have this idea of true positive, true negative, false positive, and false negative, and these things with recall and precision. And so this stays the same as before. And then evaluating models. And so we have two fairly interesting lectures here that you can look at about recall and precision, and this is more general for machine learning, but it's a very useful trade-off. And so you see these curves, and you can understand why these methods are useful and sort of how they're applied to other data sets, because understanding these methods is important in imaging as well as in lots of different areas. And so the more different examples you see, the easier it is to kind of understand what these are really related to. So if we go back to sort of a practical example again of these curves, and this is then from one of the possible projects. I don't know if anyone was interested in it, but this was then looking for calcified tissue in mammography data. And this is then very interesting mammography data because it's phase contrast using a method called DPC, which means you have multiple channels of information. So you get like a color X-ray image, sort of. So you have sort of an absorption piece of information, a scattering piece of information. And the goal is to identify these calcifications from the background. And so we have this ground truth, which has been manually labeled. We have these absorption and scattering components, and we want to come up with this image. And so if you apply a very simple threshold to the absorption image, you come up with some of those regions, but it's a pretty poor approximation for the things that you're actually trying to come up with. So all of this is from earlier lectures. This is just another example of how you use it. You can then look at these ROC curves and then see for various threshold values how well you segment the things that you're looking at. And you can see here that the trade-off between precision and recall is pretty drastic. And at almost no point do you get very high precision. So the images that we're looking at are very poorly suited for directly applying a threshold. We need to do some sort of transformation in order to get a better performance out of them. We can then compare the two channels. So we have sort of absorption there and scattering there. And we see that scattering is already much more useful than absorption if we just apply a threshold to one of the channels. But because we have both of them, we can start to combine the information together. So this is where you then have two thresholds that you vary between different values. And so you get kind of this 2D set of curves. And you can take the highest point on the curves as sort of how much information you can extract. And so you start to get a point where you're looking much closer at the information that you're trying to get and getting much better results because you're able to combine these two channels of information. So now, how is this related to what we're doing now? And so what we saw here in these slides is that we have this ROC curve. And what this is doing is this is focusing just on the image data itself. And so it's taking all of these calcifications as if they were single pixels. So is this pixel classified correctly or not? And that's what we have really been focusing up until now on. How is this single unit, single pixel classification working? While in fact, for many of the applications that we'll do later, it's much more important if you're building something to detect breast cancer or to analyze these images that you get the accurate number of plaques or number of calcifications in the breast tissue. And if you miss 1 or 2 pixels but get the right number, that's much better than getting a higher percentage of the pixels but the wrong number or the wrong average size or a wrong other parameter. And so this is kind of the transition that we're making, is away from just trying to do the best job on a single pixel basis to trying to get the best numbers or statistics out of the sort of analyses that we're doing. And so obviously if we have a very bad segmentation, then no amount of tweaking with the single component analysis, as we call it, will improve that result. But we can't focus anymore just on the single pixels. We start having to look at sort of the bigger picture. And so groups of pixels and the analysis that we can get out of these groups of pixels. And so the motivation behind this lecture is how can we start to quantify things that are a little more physically relevant to us? Because we've never been particularly interested in pixels for themselves. We're interested in, how do we quantify sort of where and how big the objects inside the images are? How can we start to say something about shape? And so, do you have round objects? Do you have very elongated objects? Do you have spiky shaped objects? Because that might have a different meaning. How can you compare objects of different sizes? And so if you look at kind of very simple metrics where you're looking at area or perimeter, if you have an object that's very small, the area and perimeter will be very small. And if you have an object that's very large, the area and perimeter will be very large. And so how can we get something where we can say, even though this object is much larger, this metric, it has the same shape as this other object? That if you just scale it up or scale it down, you don't necessarily want all of your metrics to change. You want to have some scale and variance way of quantifying something. A small car can be boxy and a large car can be boxy, but being boxy has nothing to do with the size, it has to do with the shape. And so how can we start to come up with things like that, which let us know something about the shape of the object? So how can we start to compare different images? And so when we look at experiments where you have sort of before and after, or you have specimens taken out of different groups, how can you compare what is happening in these images? And so, if you have the shape analysis and you can do something with the individual components, does that help you to actually compare the two images? And then kind of the last part, which is slightly less relevant for this, but sort of how can we then take the objects that we have and start to do other things with them? And so many of you in mechanical engineering will use imaging as a means to get better input for things like finite element simulations. And so rather than drawing a model yourself, you take a image, generate a mesh out of it, and then put it into a finite element simulation. And so this requires some other processing steps that we haven't really covered yet that we will start to talk about in this lecture. This is then also important for making pretty pictures. And so we had code that did this before in some of the exercises where it just showed you the pretty rendering. So for any of you who did the fossil exercises, you saw that. And here we'll go into a little bit of detail on how that actually works to understand what those steps are. So in terms of the outline, we have kind of the motivation. We'll talk about object characterization, volume, center extents, anisotropy. And then in more detail, shape tensor, principal component analysis, this ellipse or ellipsoidal representation. So how do we actually interpret all of these things like shape tensors and extract something meaningful from them? The scale-free metrics, anisotropy, oblateness, and then finally these ideas like meshing and marching cubes and surface area and what those mean and how we can do something meaningful with that. So to kind of go back to some of the original examples we used, you perform this huge experiment and you've done all kinds of filtering, you've now done really, really good segmentation, but you still have a huge amount of data. You still have, 1.7 gigabytes of data per sample, and you're not necessarily any better off answering the question you originally had. You want to see how big the cells are inside the tissue, and now you have, a billion pixels classified as 1 or 0. Certainly you're a lot closer than you were before, but that's not telling you anything about the cells or how big they are. You need some other analysis steps in order to actually extract that. And so this is where this lecture really comes in, is how can you now take everything that you've segmented down and turn that into something you can use to say, this is how many cells there are, this is how big they are, this is how they look, and kind of come up with a summary of what's going on in your sample. And so when we look at what we wanted in the first place, it's always this single number. So volume fraction, cell count, average cell stretch, cell volume variability. And what we have is tons of numbers, or tens of ones and zeros. So how do we make that jump? And so one of the most important tools that we have for this is called component labeling, or connected component labeling. And this, if you've done the exercises in KNIME, and potentially some of the Kaggle workshops, you've already used this tool, but we haven't officially covered what it does yet. And so what the idea of connected component labeling is that you try to connect, or you label all of the components inside of a graph that are connected together. And so what we have over here in this example is a graph where you have all of these dots as nodes on the graph. And what we want to do is see which nodes on this entire graph are connected together. Or alternatively, you can look at it as another question where, is this beginning node here connected to that node there? And so obviously, if they're right next to each other and there's a line between them, it's very easy to say it's connected. But when you look at an image like this, it's quite difficult to just look at it and say if these 2 points are connected. And so this is what this technique lets us do, is it allows us to take a graph and show how well connected it is. And images can then be seen as graphs, where each node is a pixel, or each node is a pixel that is turned on, and the lines then represent the neighborhoods that we talked about before. So that when you have, yeah?
Do you decide with respect to the color of the pixel if they are from the same object or not?
No.
Then how do you decide?
So
If they are connected.
So with the color of the pixel, so like the intensity.
Yeah.
Yeah. So with the intensity, we make a segmentation.
Uh-huh.
And we use that usually as a very important feature for making the segmentation. Once you've made the segmentation, your image has become all ones and all zeros. So you have no color information anymore. And when you do this connected component labeling, you don't use any color information.
Okay.
All you have is a giant list of ones and zeros. And what you want to do is find out where is the first object, where's the second, where's the third. And so that's quite an important step that you take, that you don't go back to the original grayscale data or a filtered image or anything else. This is just focusing on the black and white pixels that you have. And so all of the pixels here are white. And really the goal of this is to not just have black and white, it's to then have groups of pixels. So sort of like the k-means clustering we covered last time, where you now have different groups of pixels and each one of these groups is connected together. And none of the groups are connected to each other. And so that's really the idea of trying to do this. And so here we have this example with a graph where we try to run this analysis there. And so what we do is we have a component labeling algorithm. This is more for your own kind of visualization. This isn't actually how it's implemented for most of the image approaches. But you have this Brushfire style algorithm. And so basically you take one of the points that you have and you look at all of the other points that are connected to it. And if it's connected, you add it to your group. And so here you see that the first iteration just adds this point. And if you do 10 iterations, for example, then you go to adding all of these points into your graph. If you then grow from the last point 10 iterations, it looks this way. And you can start to see how these structures evolve. And that, for example, these two pixels aren't connected after 10 iterations with any of these other structures. We see ultimately that they are connected, but it takes more iterations for us to get there. And so when we look at this in the image world, we can do the very same thing. And so now we have sort of a segmented image. And so this is like the cross that we had before, where sort of the cross was foreground and this is background. And now we're looking at the background components. And we start off with a slightly different beginning point. And so the first thing we do here is we assign a different label to every image, every pixel. And so in a very simple approach, we just assign the label as the position. And so, this is 1, 2, 3, 4, 5, 6, 7, 8, whatever. Everyone has a unique label. And what we do is take all of these labels and sort of condense them down. And so figure out what is the smallest group of these labels where none of them are connected anymore. And so we start off at each point and we check all of the points in the neighborhood. And so that's all of the points where these connections exist. And we set the label of the point to the minimum of all of the labels that it has seen in its neighborhood. And then we repeat until no more labels change. And so this runs until it converges, and it will always converge. So there'll never be a point where you're oscillating. Yeah?
You have to repeat it because it's basically like the minimum point is decreasing as you go along, so then you have to go back to vertical and cycle up.
Yeah. And so actually you don't ever have to do any of this yourself. This is all inside of single functions that you call. And there's, thousands of different implementations of this algorithm. But this is just the idea, so that when you're running these kind of analyses, you know sort of what's going on. And so that we see here, if you plot all of the different numbers, you can see all the different indices with these values here, that they all have a different ID. And after 2 iterations, you've kind of started to color some of these the same, but you haven't changed very much. After 3 iterations, you're starting to group even more. And after 4 iterations, you're only left with 4 distinct groups. So here, after 4 iterations, it's done. No more labels are changing, and you've now divided your image into 4 different groups, and they all have the same label. And so this can take a very long time on very complicated images. And as you see that if there's just one point that are connecting 2 images, then you can have something like, or 2 very large regions, then you can have the 2 large regions done, and then the 1 point connecting be found, and then all of that region needs to be relabeled because you now have this 1 point that's connecting them. And so when you're dealing particularly with very large 3D structures, this algorithm can take a long time to run. And it depends then a lot on what pixels are in your image and how your segmentations look and how many different objects there are to find and a number of other parameters. But the algorithm itself is fairly simple. It's only the implementation or the actual execution of it that can take a very long time. And this is to sort of make you aware of what's actually going on when you use a tool like this. And so, we can take a component labeling on an image. So we have like the cell image we were looking at before, and we can perform a component labeling there. And so now all of these components are labeled as, or all of these objects are labeled as different cells, which then allow us to do things. So with erosion and dilation, or these morphological operations, we could use them to get rid of small objects, but it has consequences, or why are erosion and dilation not ideal for getting rid of small objects?
Change the actual shape of the object a lot.
Yeah.
If it's really small.
Yeah. So you change the shape of small objects a lot, and you change the shape of large objects a little bit. And so if you only want to keep the larger objects, doing a morphological operation isn't necessarily the best way to do that, because you'll change the shape of your objects in your image. Usually it doesn't change it for large objects very much, but you do cause things to be changed. Whereas if you take component labeling, you can then say, I don't want to keep any components that are smaller than 25 pixels, and you haven't changed the larger components at all. And so here we have a labeled image. We have a bunch of small dots around the image. We then say we only want to keep the cells larger than 25. So if you look at this histogram of cell size, there seem to be a lot that are very small, and then some that kind of pick up there. And so if we keep everything above 25, we're probably keeping most of the larger objects. Can anyone think of when morphology would be better than connected component labeling? I mean, why wouldn't you always do a connected component labeling and throw away small objects?
And small objects are important.
Yeah. So that would be one, but then you would probably keep them in both cases. Can you think of circumstances where you would sort of need to do morphology first in order to...
There's like tiny specks of noise or bad segmentation results that you want to get rid of.
Yeah. So in this one, we have the tiny specks sort of floating around, and we can use component labeling to get rid of those very well. But there are a few cases where those tiny specks cause a major problem for component labeling. Can you think of what they might be? So right here, all of the tiny specks are sort of free floating and far away from other objects.
Edges.
Well, so at the edges, I think morphology would tend to do worse because then you don't have as much neighborhood information for the thing that are at the very border. And so with things on the edges, component labeling might work a little bit better. For counting and correcting for them, there's some different things you have to take into account, but typically that's not a huge issue. Yeah?
When they're too close together, it might clump it all together to one big.
Yeah. And so when you do component labeling, if you have one pixel that's connecting two giant cells, the component labeling will join these two objects together. And so now you have one object that's twice the size of all the other objects. And so if you don't do an erosion or some sort of opening operation first, you will end up with one large connected object that you will somehow later have to decide how to disconnect. And so that's where you sort of have this trade-off. If you have a bunch of free floating pixels, you can do component labeling and get rid of all those objects because they all just show up as tiny objects. But if your noise happens to show up right between two objects, then erosion or dilation will do a much better job of getting rid of that, where component labeling won't get rid of that. And so that's one of the things to be aware of with component labeling is that it's incredibly sensitive to objects that are close together. And that having one pixel can be the difference between having a structure that's connected and one that's disconnected. And so that makes a huge difference when you're doing these kinds of analyses. And depending on what kind of your images you're looking at, that can be a very, very different sort of problem. And so if we look at the exercises or the data set for today, because that's the one I sort of am most familiar with. It was the one right before that. So that we will look at structures like this, and so our goal is to ultimately find these objects. And we see that when they're identified like that, it's quite easy. Component labeling works very well for identifying the different regions. But when we have a segmentation or a structure that looks a lot like this, and we want to disconnect it, then using tools like opening and closing can help get rid of a lot of these tiny structures that might be in between objects, where component labeling would put everything here in the same group. You might have a separate object there, you'd have some tiny ones here, but all of this would get clumped together. And once you have that all clumped together, it's very difficult to sort of pull it apart. But if you can break through a lot of those boundaries and do the morphological operations first, then you can do the component labeling and find the different regions and say things like, this is kind of round, this is a cell, this is very elongated and funny shaped, this is definitely not a cell. So that when your tasks are classifying these things as cells or not, it's much easier from these regions than it is from looking at a big giant clump or something. And so, if you did enough morphological operations here to get rid of all of these tiny lines, you'd probably damage your cells quite a bit, or damage the shapes of the cells a lot. But if you have that and you then do shape analysis or some of these other things that we covered today, you can easily separate these junk or strange shapes fragments from the round cell objects, because you'll have a number of different criteria that you can then apply in order to make that separation. Yeah.
So, can you go before? Yeah. What's the relation? Like, this is the example.
Yeah.
Synthesized. You did it manually of that image in the next slide. It's like to
This one.
yeah. Like for labeling, it's like it's the same type of image. It's like when you apply component labeling to the next image,
Yeah.
it's the same thing. Right? You don't change this image before. Like you did directly apply the component labeling, right?
To this one.
Oh, so okay. And how can you see the connections here? Like in that image, you have the connections. Like you can see the connections.
Yeah.
Like the lines.
And here you can't see the connections.
Yeah.
So what the connections are this neighborhood. So that we talked about with the morphological operations, so that every pixel has a neighborhood.
Yes.
And so we have connections here. We show this explicitly so that you can actually see how this kind of propagates. But with a normal image, the connections are just its neighbors.
Just
Yeah.
And like you said, like how many pixels? Okay.
Right. So you have different definitions of the neighbors, and when you call the component labeling functions in KNIME or Python or on these Kaggle notebooks or R, you have the option to tell it which neighborhood it should use. So some of them give you more flexibility than other ones of saying exactly what the neighborhood should look like, but all of them, or almost all of them, give you the ability to specify what things should be connected or not. And so when you look at a normal image, sort of zoomed in, you can kind of imagine these lines as connecting all the different pixels that are next to each other.
Oh, okay.
So I don't know if we have a higher resolution image that you see. Yeah, so that if you zoom into one cell on this object, you then have this as the pixels. So these pixels are all 1. The background pixels are all 0. And then the connections are implicitly between all of the pixels where either the edges are touching or the vertices are touching, depending on which neighborhood you're using.
Okay.
So that there's a line from here to here, there's a line from here to here, and sometimes there's a line from here to here.
Okay.
But we don't show all of that, and most of the algorithms don't really have that shown because the graph representation is very big and complicated. It just makes it a little bit easier to visualize what's happening with the actual component labeling. So that you see that it's actually kind of growing objects and it's looking at those neighbors, but if there's then a single pixel that's touching, it grows into both of them. And so I think we have an example. Do we have one later? That like here for this example. This is all part of the same cell. And right here we see that there's actually just one point connecting these two regions. But connected component labeling doesn't know that or care. It just knows these two are connected together, and therefore this is one object.
Okay.
And so we'll need other techniques if we want to say this is 2 objects, or we would want to identify that as 2 objects.
And then we can apply morphological evolution before.
Right. So if we applied an erosion before, what would that do?
It's 2 objects.
Yeah. So it would delete that pixel in between, and then you would have two separate things.
Oh, okay.
Yeah, but it sort of depends. If you have very small cells, then doing an erosion in between might also erase little parts of your cells. Or maybe this is one cell that's in the process of dividing. From here, it's very difficult to say if you would want to keep that as one cell or two cells. But you should be aware that when you apply component labeling or connected component labeling, that will be identified as one object. And it doesn't matter if there's 1,000,000 pixels here and 1,000,000 pixels here, as long as there's one connecting them, the entire graph is connected. Yep. And this is also the same logic and the same tools that are applied to things like social graphs. And so when Facebook is trying to suggest new friends to you, or LinkedIn is trying to suggest new contacts, it's doing sort of connected component labeling on the graphs of friendships that you have. And so it's looking at what people are you already connected to, what people are the people you're connected to already connected to, and what people should you potentially be connected to by looking at that. They also can use that to sort of divide up very, very large data sets. And so if you have millions and millions of people in your database and you want to store them efficiently, then you can use something like connected component labeling to break your data set into groups where each group sort of is entirely connected within itself. And so you don't need access to the other sets. And you can then process that much quicker or have that located somewhere where it's much easier to access. So this was really the challenge of getting our image from being sort of 0 to 1 to being, with a label or identity. So now each group has its own label, and we can start to perform very simple analyses. And so if we've done this connected component labeling and we want to know the number of objects in our image, how do we calculate that? This is much easier than the other questions.
Just count the ones that have the same label number.
Yeah. So you just count the number of different labels that you have. And so here, if you want to count your number of objects, you just count your number of different labels. And so it's very easy. If you want to know how many cells are in your image, you look at how many different labels are in your image, and you're done. So you just go through it and you say, this is the number of unique labels. We look at this. And so if you plot it like this, then you can see here that there's 4 objects because there are 4 unique labels, and you're done. And so if we're doing something like counting objects, it's now very simple when you've done a connected component labeling. You can then do things like count the number of voxels or pixels in each label to estimate volume or area. So the number is the area. You can then use other things to look at like surface area if you look at the change or something, but that's less important right now. And so now we take this image that we had before of the cells. We've done the connected component labeling. We've thrown out the very small objects because we think they're noise. And so now we're left with just the different cells. And so all of them are colored with a label between 0 and 80. We can count the cells. That's fairly easy. And what we really want to do is be able to do some kind of analysis about it. So can we say the average shape of the shell, or what do the shapes of the cells here look like? How big are they? And how can we then compare this eventually to another image or another cell? And so how do we start? And so what we start with is we pick a label and we focus on just that. And so now we make kind of a new black and white image where if it's inside the label, it's 1, and if it's outside of the label, it's 0. And so this is then taking the very first cell. And, the very simple metric we can identify from this is then the center of mass, or the center of volume. And so this is just the average of the x values in the cell, or the y values, or the z values, all put together. And so we can show here that this red cross shows you the center of mass for a cell like this. And so that's a very simple metric that we can now extract, so that rather than having a group of pixels, because each one of these pixels has a location, deciding which of those locations is best for the cell isn't easy. And so now we can just use the center of volume, or the centroid, as the position for the entire object. We can then do things like center of mass, and this is then where we get back to looking at the actual color or intensity value in the image. And so if the intensity value in the image corresponds to something important, then you can use that as sort of a weighting factor. And so if the intensity of the image is like the density of your dye, or the mass of the bone that you're looking at, then maybe the center of volume isn't the most interesting parameter, because as we see in this cell, the density is much higher near the borders than it is in the near the upper sort of right than it is in the bottom left. And so what we want to do here is identify where's the center of mass. And so we do that by doing this weighted average over all the different axes, so that we now have a center of volume that we can compare to the center of mass. We can now look at other simple analyses like the extents, which is sort of the same as the bounding box, for those of you that have heard of that term before. And so for a cell, this is basically the minimum in one direction, or the maximum in one direction, minus the minimum. And so it's the, yeah?
But once you did the segmentation, you lost all the gray values, all the grayscale.
Yeah.
So how do you know, once you get this blob, it's kind of monolithic, how do you know where to put more weight?
Oh, this is where you combine this with the original image before. So one of the ideas that I think we've mentioned before is this idea of using like a mask. And so you can use this as a mask on your original image, where you only look at the values that are inside of this mask, and then you do an analysis on that. And so that's how you can do something like a center of mass. But of course, if you are just looking at the grayscale values, then the center of volume and the center of mass are exactly the same thing, because they all have the same weight. There's no shift there. It's only when you add new information to that that you can start to get more out of it. So this is the extents. This is not something that you need any more complicated analysis for, or any of the original image data. You just take sort of the longest dimension in each direction. And that's sort of what it looks like. And now we're starting to get lots of sort of simple information about each object. And so we're able to measure a number of different features on this cell, but a lot of these features that we've measured aren't really what we're looking at. And so for making a graphical representation, it's very helpful, because if you know the extents, you can draw a bounding box, which then gives you a very simple way to represent your cell if you don't want to keep all the pixels, or if you just want to show all your cells in a graph or something. But no biologist has ever asked, how long is a cell in the X direction? Or that's not a very common question that you get. And so we want to be able to take this and turn it into something a bit more meaningful, or a bit closer to what we're actually looking at. And so this is where we start to get into sort of new metrics, or more complicated metrics like anisotropy. And so has everyone heard of anisotropy or isotropy before? Okay, so we have some people that aren't as familiar with it. And so it's a complicated sounding word for a very simple idea. And so basically what it means is how similar is what you're looking at in different directions. And so if you have something that's isotropic, so a lot of times with image acquisitions, you'll talk about isotropic pixel size or isotropic voxel size. And what that means is that it's the same in every direction. And so one of the things about sort of computed tomography or synchrotron imaging that makes it very interesting is that you have an isotropic voxel size, or you can have an isotropic voxel size. And that means that you get the same resolution in every direction. Whereas when you look at sort of medical imaging, you very rarely have isotropic voxels. So you often have very good resolution in one plane and very poor resolution in the other plane. And so there you have to kind of pick which plane is the most interesting for you to make sure that that overlaps with the areas that have high resolution. And then the other areas that have lower resolution, you need to ignore more. And so, if you're looking at a human, people are, not completely isotropic, but cells are very isotropic. And so you'd actually like to have high resolution in every direction, and so it doesn't fit well to have a really anisotropic technique on a isotropic sample. But because of the restrictions of dose and time measurement, you have to apply that. For us, what it means is that when we look at these cells that we had before, we have sort of these extents now. And one of the things that we want to say is sort of, we don't want to say the extent is 2 millimeters in one direction and 2 millimeters in the other direction. It'd be nice to say the object is round or the object is elongated. Does it look more like a circle or like a cigar or pencil or rod? And that's what isotropy gives us. And so we have the ability to say, kind of, is it tall and skinny, short and fat, or perfectly round? Unfortunately, because the definition of anisotropy is also very vague, there is a lot of different ways you can calculate it. And so here are 4 different ways, but the more literature, the more books you read about it, the more different ways you'll see for calculating more or less the same thing. And more, what you have here is really this idea of the longest side versus the shortest side normalized by some factor. And so here it's the longest side over the shortest side minus 1. And so what you can do with these metrics to kind of visualize is take, a very simple example. If the sides were exactly the same length, you'd have 1 over 1 minus 1, 0. So this one would give you 0 if it's exactly the same length, which is good because anisotropy means it's different in different directions. And if it's 1 here and 1 here, then it's the same in both directions. The other thing you can do is kind of the limit as the longest side goes to infinity and the shortest side sort of goes to 0. What does this term go to? And so here, as sort of the longest side gets bigger and the shortest side gets smaller, this value is unbounded. So this could be, millions or billions large. And so this anisotropy can get kind of infinitely big. And with something like this, we can do that same approach that we've done before, where 1 minus 1 over 1 is 0. So you still start off at 0. But if you make the longest side infinite and the shortest side 0, you end up with 1. And so even with the most anisotropic elongated shape you could ever create, the highest anisotropy you will get there is 1. And so all of these give you sort of different balances between being very sensitive to changes in the length and giving you an accurate representation of how anisotropic an object actually is. So I think we'll take a pause there before we get to the rest of the material. Are there any questions on that so far? No? Okay. So feel free to take